Welcome back. We left off last time having hooked up the 6551 chip to good old JCM-1 to get basic serial communication working. And we were able to do it so that, you hit the enter key and it spits out a fairly simple string on the screen there. I can't talk today, but that's okay. If we want to be able to do anything with JCM-1, we need to have some sort of basic operating system in place that allows us to view memory, store things into memory, and then execute memory. So the past few weeks, I've been spending some time whipping that up, and we're going to look at that today. So here we are on the screen. Good old JCM-1 is up and running. You can see now we have a nice new welcome screen here, and it's just showing us a memory location. It's pretty straightforward how to use the monitor that I put together here. It has three very simple commands. The first is the list command, where I can type L for list, give it a memory location, hit enter, and it'll show me what's in that memory location. Let's look at the first bytes of ROM code. There we go. Very simple. The next is going to be the store command. Obviously, this command allows us to put bytes into memory, so I could store into 1, 2, 3, 4, the bytes 1, 2, 3, 4, 5, 6, 7, 8. And if you look here, it's a B8AAC. It's just random stuff because it's just the boot up status of the RAM. But after I put that in there and then do list 1, 2, 3, 4. You can see now it's 1, 2, 3, 4, 5, 6, 7, 8. It's the bytes that I put in place there. So we have list and store working. So what's next? All there is execution. But before we execute something, I got to put something into memory. So let's do that. And I'm going to do this to show you no tricks up my sleeves. This isn't anything in ROM. This is something I'm just going to put directly into the monitor here. It's going to store it, and then we'll execute it. I'm going to put in some code at 300, which is pretty standard starting location for 6502 code. So we're going to list 300, so you can see the data that's in 300 there. Then I'm going to go here and copy this code out. We're going to paste it. Hit enter. We have our code in there. So now if we look at 300 again, see, this here matches this here, and it's different from what it was before. So we have stored that code. Now we're going to execute it. Go 300. Hello, world. Pretty easy, straightforward. Now I don't have an active command interpreter when another external piece of code is running, and this code is a very simple loop, so I can't do anything to get out of this. All I can do is hit reset, but it resets and comes back. That's really all there is to the user interface of the monitor program. It is really straightforward. It's like very similar to the monitor program in an Apple I. Not too complicated. It gets you just far enough to get stuff working. But now we get to look at potentially the boring stuff if you're not into programming. And that's the actual ROM code itself. Now I am going to gloss over some of this because it's programming and it can get very dry and boring very quickly. I'm also not the best programmer. If you see anything that I'm doing really weird, not following standard 6502 or 65C02 convention in my programming, call me out in the comments below and let me know, hey Joe, you did that wrong, and so I can make the code better. Again, because I'm such a bad programmer, I'm sure I'm not doing things in the optimal way, so we'll see. So let's go ahead and bring the code up and go up to the top here. First off, this is the monitor name, blah, 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 blah. I've been working on it for just a couple weeks, not too long. Let's go through the zero page locations. These are just pointers to where the command interpreter is inside the command buffer. A pointer to string locations for outputting, for printing strings to the screen immediately. This is the cursor location for the monitor, basically where it's currently doing something with memory. This is a little index byte that's used during the address decoder. More address locations for when we're storing something, because we need to have the address for where the monitor is operating, the address for where the store routine is working separate for restoration during errors and things, whatever. Index, this is a quick little index thing that or index byte that I put in there so I can keep track when I'm parsing bytes during the store code, so that it can know the difference between a single character byte like F and the difference and a 2-character byte like FB, you know. Helps me keep track of where I am. And then this is just a little check value for when we're checking to see if the input we're doing is or is not hexadecimal. The command buffer is at location 200, of course, because page 0, page 0 page is where all the extra registers, if you want to call it, that the 6502 uses those quick accessible addressable locations are, and page 1 is the built-in processor stack. It just uses that location automatically for our processor stack. So I decided to go ahead and put the input buffer at 200 here. Some quick constants here, or quick hardware locations, so we know where the ACI is. And here we come in. So when we start, basically what we do is we start up we initialize the serial chip, and then we immediately print out the hello message. And this uses ANSI right now. It uses console commands, escape characters, basically, since I'm connecting to it right now through serial communication. There's a serial connection through the terminal here. To clear the screen and do all that. And you can see that like when I put stuff in here, if I reboot that, it just clears the screen. Then, we initialize the monitor. We set our monitor location to E000. As you can see that if I list and get it racked up there, if I reboot, takes me back to E000. It's just I wanted some location to start off when when it loads up. I could make it 0, I could make it 300, I could make it whatever I want. I just decided to go with where the ROM code is. I don't know, just seemed appropriate. And then we print the command prompt. When we come back to the command prompt, we zero out where the command buffer is, because when we're coming back to the prompt, we had no command in the buffer. So we set that back to 0. We advance a couple lines, print the monitor cursor, and send all that out. And then we get the user input. I'm gonna gloss over this real quick, but yeah, get a byte. Is it escape? If it is, it bombs. If it's not, then we go to see if it's carriage return. If it's carriage return, that means we actually have something in the buffer to go parse, so then it goes and parses it. Or is it a backspace? Then we go deal with that. If it's none of those, then we need to go ahead and increment the buffer, move everything forward, and then go back to getting another character. If it's, here we deal with backspace. If it's backspace, yeah, basically we decrement the pointer, and then do a little magic here to delete the character on screen, and then just go back and get another character. Parsing the command, the first thing here I do is I get an extra return just so it clears the line. So any responses won't be directly on the line that you were typing in on. If the pointer's 0, that means it was a blank input, so we go back to the memory. Otherwise, we get a byte if it's a space. This stuff right here basically helps determine if there's lots of spaces in the buffer, and deletes those spaces and automatically increments the pointer as we move along, so that we're not having to deal with that. If we go through all that and reach the buffer in, we bomb out. And then, we check for the commands. Convert to uppercase, and if it's go, then we go to go. If it's list, it's go to list. Store, it's go to store. And if you go through all of that and fall all the way through, it means the user did something wrong, so we just print an error and go back to the prompt. Listing, there's two kinds of lists. One is list immediate, which basically just grabs the current monitor cursor, goes and lists 16 bytes in order, and then sends it out. That's this here. However, if you explicitly type an address, what this does is it checks to see you know, if there is or isn't an address listed there, decodes it. Then once it's decoded, then list immediate will show what's in the address you specified. The go command, which is execute, is really easy. Basically, we just decode what's on the command line and then go do it. I might need to put a little bit more context checking here, but I believe address decode does all of that context checking to make sure there's no spaces, there's no non-hex characters, blah, 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 and removes them before putting that on the address, you know, monitor cursor location here before execution. So I don't think it matters, but I haven't done a huge amount of extensive, you know, death checking, you know, crazy user input checking to check that. But, you know, that's not that critical for a basic monitor program. Here's the store command, which is very, very, very long. Long story short, what this does, you know, this stuff right here is all about the same as everything. This just parses the beginning of the store command to determine whether it actually has an address or not, all of that stuff. If you provide it with a colon but no address, if you just ask colon, it will start storing at the immediate memory location. And that's good for when you're programming lots of stuff back to back. You don't have to know where you are in memory and retype the address. You can just hit S colon and start giving it more bytes, and it just takes up right where it left off. That's pretty standard. Checks whether there's colons in there. If you don't provide a colon, it makes it a little bit harder to parse the ending of an address and the beginning of byte data, because they're all hexadecimal values. So I require the colon in there, and if it's not in there, it bombs out. If I don't find a colon in there, your store command is invalid, and I'm just gonna ignore it. This is lots and lots of craziness, which I will leave as an exercise to the reader. This piece of code is what took me the longest. I actually had to create a flow chart and write this out in a flow chart of how the logic should function before I could write this code. I tried to just write it and keep it in my head, and I could not. I had to, you know, check for every possible combination, flow, you know, design that all out, then write each piece of this, each phase of this, in order in section, based by how it cleared the flow chart to get this to work. It's probably more complicated than it needs to be. But based on the way I laid it out, the way I logically thought it out in the flow chart, I don't think it can be simplified much more. I tried a lot, because you can see there's a lot of repeated code here. Like this code here is very similar to this code here and stuff. But without using a lot of subroutine calls to do some of these basic tasks, it would, you know, it just makes sense to just put the code in there and just type it twice, because, you know, we need to do this, but then immediately after that we're doing something else here than we are here for the different, you know, the different scenarios we have to go through. Subroutines would probably take up slightly less space, but they'll probably be a hair slower as well. I don't know. I might rewrite it later to use subroutine calls for some of these common things that are done. I don't know. Haven't decided yet. Right now I'm focusing on performance more than space, because, you know, my long-term plan isn't to have a very complex operating system in this machine, just enough to get it bootstrapped and up, and that's it. And then everything else after that will be, you know, code that you load in and do something with on the side. So, but I digress. Anyway, address decode. This is inspired by the Woz himself, mostly on the way some of the math worked. It wasn't a direct copy of Woz's code from the Apple I monitor, but it was pretty close. But yeah, basically what this does, it just determines whether the character's hex, determines whether it's receiving a single hex character like F or two of them, FF, and then decodes that and shifts it properly, shifts that out properly into the Mon-Curlo location by calling this subroutine here. I put that portion in a subroutine because this piece of code is called by more than one thing. It just made sense to separate it out. Kind of like I didn't do up here, but you know, whatever. So that's what that does. Is hex. This is a very simple code. All of this does. I got this partially from Woz and partially also from the 6502 enthusiasts group on Facebook. They helped me figure out some of the math on this here. But basically, this just goes through and determines whether it is or is not hexadecimal. And then what it does is stores the result of that in this location here. So that when I come back, I can just say, hey, go check if that's hex. It comes back to me telling me whether it's hex or not. Then I can do further parsing. To nibble. This one is almost, I'm sorry Woz, but this is almost a direct copy of your code, almost like line for line, because looking at it, it's pretty much the only way to do it. I mean, you could do it on more complicated ways, but this is just elegant in functions. So basically, yeah, this just takes, it takes your digit, it takes your decoded nibble, say F, and then shifts the bits into position so that they're stored in the memory location correctly. This is print immediate. This is a direct copy with a little bit of modification right here from the good old 6502.org folks. Again, another suggestion from the folks out there on Facebooks. Basically, just because it works. This makes it really easy to put inline print commands. For example, if we go all the way back up to the top here, that's what this is. It's just an inline print command, so you don't have to do a lot of crazy like message data array indexing and stuff if you're just putting a few messages here and there. This makes it a little easier to code. So going back to that, effectively what this does is when you call this, it goes out and determines where the call came from by looking at the stack, then does some math with the stack, pushing and pulling stuff off of that to get the bytes immediately out of memory, immediately after where the call came from. And then when it's done, because it's zero terminated string, it knows how many bytes the string had. It increments that stack location that it pulled out by that amount, pushes it back, then JSRs, or then returns. And when it returns, then it will have printed the stuff out to the screen and comes right back to where it was. In this specific case, it actually does a jump because it's doing these pulls. It doesn't actually push it back out onto the stack. I take that back. So then but then it stores it out to this string out pointer location, which is that modified location, so that you just basically jump directly back to there. So you don't have to do an RTS, but that's fine. Print monitor cursor, this uses some of those previously defined routines and some ones that are below to just print the current monitor location where you're listing or executing code or storing code. Print hex, again, one and only Woz. Again, why? Because the code works. I did modify it a little bit because his code was designed, was it this I modified? Or was it something else? It might have been this I modified, but yeah, plays around with the offsets and the math there to print the hex, the hex byte directly to the screen. Whatever's in A, it prints it to the screen. So, of course, we're doing a little fall through trick. If we're printing hex, which means we're going to be sending that out. We're going to be sending that out to the screen. So this doesn't have a return. It falls right back out into ACIA send byte, which has the RTS on it. ACIA 0 send byte just sends a byte out the ACIA. You might consider this actually to be a serial output driver in a way. Right now, the entire ROM is coded to just send through send byte, but I could code it to send through a genericized vector that points to whatever you want the output, your standard output location to be. Similar to the way like the Apple II, like if you hit PR1, it sends it out port 1, or PR2 sends it out, slot 2, and then if you hit PR0, it brings it out to the screen. I could do something similar with that, with a kind of a redirection there. But right now, I'm just sending it straight out. Anyway. But yeah, just pushes A on the stack, asks the AC of its status, asks to see if it's full, if it is, if the buffer's full because it's sending a byte. It just loops until the buffer's not full. Then once it's not full, it kicks the byte out, then just comes back. The cool thing about this is this does all my wait loops for me. I don't have to do anything complicated there. When I want to send a byte out or get a byte, I just go call and get a byte, and it'll sit there in a loop until a byte comes out, which is pretty nifty. Same thing for the get byte. Well, that's send byte, but get byte is the next thing too. It does exactly the same thing. It's like, hey, ACIA, what are you? If the buffer's empty, it just keeps asking in a loop until the buffer receives a character, and if it does, it gets it and sends it out. Pretty straightforward. There's that initialize code we talked about for the ACIA. Nothing fancy there. Just sets up the serial chip, and then we have our vectors. I have it set on all locations just to jump to the beginning of code. That's pretty much all there is to the code. Now that we have that code up and running, I can start to do more advanced things with it. So we can start actually write applications. It's pretty bland, but I could write just about any math package, for example, that the 6502 could calculate. If we wanted to calculate pi, I could write that and throw that in there, and it would calculate pi. If we wanted to do, Towers of Hanoi with on-screen fake graphics using ASCII or ANSI characters, ANSI art, we can do that too. It has the ability to do that. So we have that full capability. Because we have that now, I can start playing around with adding more advanced input-output graphics and audio to the computer, and this is where we start to have fun. We can put the chip on it and then start smacking the chip by just typing stuff into memory locations and executing it and seeing what happens. So we can do some basically in-machine testing. So that's going to be really the next step, is adding some chips and playing around with them. Not sure what chip we're going to add next. Maybe a 6522. I may add a sound chip. I know I keep saying about the sound chips. I have ADD. I love flashy, bright, noisy things. But maybe we'll just do a blinky light with a 6522 to confirm we can do that. Might do a built-in keyboard. I'm not sure, but yeah, we're about at the point where we need to move on and really start making this its own standalone machine. Well, that's a pretty quick video. That's all I had for today. If you have any comments, leave them down below. Let me know. I hope you enjoyed the video, and remember, 8 bits are all you need.